Great. So our next speaker is Yossi Gilad from Boston University and MIT. He's going to be describing us some of his recent findings on measuring the deployment and security of the RPKI system.
Thank you for this introduction. So, so this talk is all about the RPKI. And so let me first briefly introduce what the RPKI really is. So the resource public key infrastructure, or the RPKI, maps IP prefixes to the organizations that own them. And it is really intended to achieve two goals. So the first is to prevent prefix and subprefix hijacks. And the second one is to sort of lay the cryptographic foundations that are required for more advanced mechanisms like BGP-SEC in order to protect against path manipulation attacks. So how can RPKI protect against prefix and subprefix hijacks? Well, consider the following scenarios. So here we have Deutsche Telekom at AS3320. And Deutsche Telekom has a prefix 91.0/10. And so they advertise that prefix to their peer at ASY. And ASY continues and relays that advertisement to their own peer at ASX. So now ASX learns a path to reach the IP addresses within that prefix. Now, let's say that our attacker at 666 does the same. So it sends an announcement for the same prefix. And now ASX learns two competing routes for the same IP prefix. And in the normal case, it would actually send its traffic to the attacker because the attacker's route is shorter. And so it appears to be more attractive. But Deutsche Telekom had actually used the RPKI to issue a Route Origin Authorization record, or a ROA. And the ROA specifies that Deutsche Telekom at AS3320 should be actually the origin for the IP prefix 91.0/10. And so ASX can now use this information and perform route origin validation. And so they can identify that the attacker's route is invalid, discard it, and send their traffic down the correct path. So in this talk, I'll actually focus on these two aspects of the RPKI. So first, I'm going to talk about doing ROV and what are the security benefits that we can gain from it. And in the second part of the talk, I'm going to talk about the ROAS and the information publicly recorded there. So, we've done some measurements about ROV adoption. And in particular, in this talk, I'm going to focus on the non-adoption aspect. And we'd want to measure how many ASs do not filter invalid advertisements using ROV. And the main challenge here is that, while ROAs are public and you can view them, the information of whether or not an AS chooses to do ROV is actually a private decision to that AS. So we sort of need to infer that from what we see. And our way to infer that is to look at the announcements that are made and propagated through the internet using route views and identify invalid announcements by comparing them against the information recorded in the ROAS. And so we can find ASs that relay these announcements. So in this case, ASs A, C, D, E, and F have relayed an invalid announcement. And so we conclude that these ASs do not discard invalid announcements. And we actually found that 78 out of the 100 largest ISPs on the internet do not perform filtering. And the reason why our numbers focus on these 100 largest ISPs is because the visibility we have to the internet using route views is actually greater in those ISPs which are at the core of the internet. So they're more likely to relay routes that we can observe, while ASs in the edge of the internet are less observable. So really, it seems that the adoption of ROV is very partial at best. So what does it mean for the internet? So in other words, what happens when under partial adoption? And we identify two effects. So the first two collateral effects, the first one is collateral benefit. And that is that an AS which adopts ROV can actually protect other ASs that don't do ROV. So in this example, consider the origin AS who issued a ROAD for the prefix, and the attacker at 666. And AS2 performs ROV while AS3 does not. And let's say that the attacker performs a sub-prefix hijack. So it announces a sub-prefix of the origin's prefix. And so AS2 can use the information in the ROAD to identify that this is invalid because 666 should not be the origin, and discard it. And that means that, that when the origin actually sends its advertisement, well, that's the only advertisement that AS3 will receive. And because it only received good routes, it will send its traffic that way. So even though AS3 does not actually adopt ROV and it did not actually discard the invalid route, it is actually protected. The other sort of collateral effect that we've noticed is collateral damaging effect. And here, what I mean by collateral damage is that by not adopting ROV, you might cause ASs that do adopt ROV to actually fall victim to attacks. So consider the same scenario, except now I've swapped, and AS2 does not perform ROV while AS3 does. And the first effect that I'm going to show is disconnection. So let's say that for whatever reason, AS2 actually prefers to advertise routes from the attacker rather than from the victim. And let's say that our attacker performs a prefix hijack. So it announces exactly the same prefix as the victim. Well, now AS2 will sort of forward this advertisement, the advertisement from the attacker, to AS3. And AS3, since it is doing ROV, will know to discard this announcement. So it will drop it. But now it is like AS3 did not receive any advertisement to reach that prefix. And so it would actually get disconnected from AS1. Now, you might say, well, disconnection is much better than sending my traffic somewhere where it doesn't belong. And it does seem that if you do ROV, you actually will know to tell the difference. But that doesn't actually promise you that you won't get fooled or that your traffic will reach the actual destination. And in fact, ROV under partial adoption can cause a mismatch between the control plane and the data plane. So consider the exact same scenario, except now the attacker is performing a sub-prefix hijack. So the attacker announces a sub-prefix of the victim. And because these are two different prefixes, the prefix and its sub-prefix, AS2 can actually announce both of them to AS3. And AS3, again, knows to tell that the attacker's advertisement is invalid, so it discards it and really decides to send the traffic in the correct way. So first to AS2 and then to AS1, except we don't have source routing on the internet. And so what happens is that the packets reach AS2, but in AS2's routing table, they are actually routed to the attacker at 666. So the attacker would actually get the traffic even though AS3 did not want them to send that way. So in order to quantify the benefits under partial adoption, we use a simulation framework. And our simulation works as follows. So we pick an attacker and victim pair, and we assume that the victim had advertised a ROA for its prefix. Then we pick an adopter set, so some ASs who do ROV. And then we measure which ASs would actually route their traffic to the victim and which to the attacker. We use an inferred links between the ASs as the internet map. And here are our results. So we quantify the attacker success rate as the fraction of ASs that will send their traffic to the attacker. So that is what you can see here on the y-axis. The x-axis describes the expected deployment among the top ISPs. So again, focusing on those ISPs at the core of the internet. and we assume that the rest of the ASs on the internet do not perform ROV. And you can see in this graph 2 lines. So the green line describes what happens when the top ISPs adopt with probability 1. So on the far right data point, the 100 point, you can see what happens when exactly the top 100 ISPs adopt, and that is the green line. And you can see that the attack is pretty much diminished. In fact, even with 20 adopters, the attacker success rate is really goes down. So we contrast that with what happens when the adoption rate is only 25%. So basically, in the farmost data point now means that we get an expected 100 adopters, except they are selected from the top 400 ISPs. So each of the top 400 ISPs adopts with probability 1/4. On average, you get 100, but now they are more spread out, and you can really see the difference here. So we've observed that for sub-prefixes as well as prefix hijacks, you can see the same sort of effect. And we've also compared between two scenarios. So first is today's status as reflected by our measurements, meaning that the top ISPs that we've seen to not adopt continue not to do so. That's the red line here. And the green line describes what happens exactly in the same scenario, except now all the top 100 ISPs adopt. The y-axis, again, describes the attacker success rate, and the x-axis describes the adoption probability by the rest of the internet. So you can see that even if all the ASs on the internet adopt, because of the collateral damaging effect, the sub-prefix hijack plotted here actually stays very effective. The attacker still manages to steal about 60% of the traffic. So really, adoption by the top 100 ISPs makes a huge difference. And in fact, the bottom line is that ROV enforcement by the top ISPs is both necessary and sufficient to provide some substantial security benefits. So the next part in my talk focuses on ROAS, and specifically, maybe the reason for why ROV is not adopted that much is mistakes in ROAS. So basically, there are ROAS that would cause legitimate announcement to appear invalid, and these have been well studied before, and we find that about between 8 and 10% of the ROAS of the prefixes covered by the RPKI are actually invalid. But I'm going to talk about some other aspect of mistakes in ROAS, which are insecure deployments. So the ROA has one more field that I didn't talk about before, which is the maximum length that the issuer allowed for the AS to actually announce. And in this case, the issuer had set it to 24. So that means that all sub-prefixes up to length 24 are allowed. But ASA, which is the AS allowed by the ROA, actually only announces a /16. So in this case, we call the ROA loose because it allows more than what you actually need. And the attacker can actually exploit that. So what can the attacker do? Well, it cannot claim to own the IP prefix, but it can sort of advertise a spoof link between itself and the ASA. And if it would just announce the same prefix, then, well, in this case, ASX would actually send the traffic to ASA because its route appears to be shorter. But the attacker can actually exploit this ROA and specify a sub-prefix. And when it does so, now traffic from ASA will actually route to it because of the more specific rule, because of the more specific match rule. So loose ROAs are actually common, and in fact, 30% of the IP prefixes that are covered by the RPKI are not protected because of that, and it manifests even large providers. So in order to sort of improve the accuracy of the information recorded in ROAS, we present ROAlert, a system that has sort of two faces to it. So one is a web interface that allows administrators to check the status of RPKI adoption in their own network and see if they are protected, and if not, why not. So it really explains the reason. And the other side is sort of an online proactive alert system that is constantly monitoring, constantly comparing BGP advertisements with the information that is recorded in ROAS, and alerts administrators about problems in their network via email. So our initial results running ROAlert are actually quite promising. We've sent out notifications to 168 operators and have reached about 40% success rate, or 40% of the errors that we've notified about were fixed within 1 month. So the conclusion from this talk is that really RPKI can be very effective in mitigating prefix and subprefix hijacks, but we have to incentivize adoption by the top ISPs, which is both necessary and sufficient to gain those security benefits. But first we must take care of the information inaccuracy in the RPKI, which is a major challenge. And for that, we've presented ROAlert, which we believe is a promising approach. So with that, I'd like to thank you and take questions.